Okay, so, and then we're going to, one more type of equilibrium has to do with what's called a Lewis acid and base. And actually, I don't want to confuse the issue, because an acid is an acid is an acid, and a base is a base is a base. But remember, our Bronsted-Lowry model only is applicable to hydrogen transfer, hydrogen ion transfer. And so actually we can identify other things that can act as an acid or a base without the hydrogen ion. So this actually expands our definition of what an acid or base is. So it doesn't change anything else, this definition. So like I said, if something's already a Bronsted-Lowry acid, it's also going to be a Lewis acid, or if it's a Bronsted-Lowry base, it's going to be a Lewis base. But the definition broadens us just a little bit. So a Lewis acid is defined as an electron pair acceptor. Remember, the Bronsted-Lowry Lewis acid was a proton donor. Now we're calling it an electron pair acceptor. And a Lewis base then is an electron pair donor. So the donor acceptor thing changed because now we're talking about an electron pair. And I think in a minute I'll show you some pictures to show you what I'm talking about. So like I said, it can describe lots of other different reactions that we might not think of as acid-base reactions. And so that's why this is kind of plopped into this chapter, because we're going to be talking about compounds that are dissolved, so they're not precipitates, but they're also different from the ion itself. So you'll see what I mean in just a second. So sometimes a Lewis acid-base reaction can only produce one product, and it's called a coordinate covalent bond. So let's look at in a minute. Okay, so lots of things that behave as Bronsted-Lowry bases will also act like Lewis bases. So like I said, if something is going to accept a proton, you kind of think of it as another way. It's like here, if you've got this molecule, and here's its electron pairs. So here's the molecule, and here's some electron pair over here, and then you've got a hydrogen over here. So you can think of it as a proton acceptor because it's accepting the H, or you can think of it as a electron pair donor because the electron pair is actually what's grabbing the hydrogen and it's donating. Instead of the electron pair being all by itself, it's kind of like it's donating to the hydrogen to create this bond between them. So it's really the same idea, just a different way of describing it. So for a species to accept a proton, it has to have an atom that has an unpaired electron. So oftentimes it's like an O or an N or one of the halogens, phosphorus, things like that. These can all be good Lewis bases because they have electron pairs that they can donate or share. Amines tend to have nitrogen. Water, of course, has oxygen. So a lot of these things can serve as Lewis bases. So similarly with an acid, a Lewis acid is an electron pair acceptor, right? So we can think of, if we think of the Bronsted-Lowry acid, it's a proton donor, like something that has a proton that gives it away. But you can also think of it at once that hydrogen is given away, now these electron pairs only belong to the molecule because that hydrogen has left. So in a way, it's like it's accepted an unshared pair or an electron pair that it was sharing it, and now it's got it only to itself. So it can, so like I said, if something was a Bronsted-Lowry acid, it's still a Lewis acid. It's just in the way you describe what's happening. And a Bronsted-Lowry base is also a Lewis base because of either of it's the action is here with the unshared pair rather than the action with the hydrogen. So it's just a different focus way of looking at it. So a lot of our cations, which are electron deficient, can serve as Lewis acids. So they can accept the electrons by taking something else away. So there doesn't have to be a hydrogen anymore. Electron deficient molecules, so like boron, I don't know if you remember, boron tends to only make 3 bonds, and so remember it likes to have 8 electrons, so it kind of has a missing thing here where it could accept an unshared pair from some other element, and so it can act like a Lewis acid. And so again, it can expand the number of species that are considered to be an acid. So here we have some pictures that'll help. So here water can act like well, if we look at the Bronsted-Lowry, we see that that water here is acting like a base because it's accepting a hydrogen. So it's a Bronsted-Lowry base. But we can also think of it as a Lewis base because it's donating this set of protons to the hydrogen. So again, this is anything that has lone pairs can act like a base. Sometimes we call this this bonding a coordinate covalent bond. So when the electron pair joins up with something else, we call that coordinate covalent bond. So you can see here, again, this is giving up its electrons to the hydrogen. So a coordinate covalent bond forms when one of the atoms provides the bonding electrons to something else. And so we have something called a complex ion. Now those that we just saw weren't necessarily complex ions, but this is an example where the ammonia is actually acting like a Lewis base because it has an unshared pair that it's willing to donate. And boron, like I just said a few minutes ago, actually has an empty space because it really doesn't, it would like to have 8 electrons, but since it only had 3 to start with, it can really only make 3 bonds well. So what happened is the nitrogen and the boron create a coordinate covalent bond, and so now we have a complex compound that's where there's this coordinate. So it's kind of weird because we don't actually have an acid and a base product. So we have a base, a Lewis base, and a Lewis acid, and then we end up with this complex here at the end. And this is called a coordinate covalent bond. A lot of positive ions will link up with these covalent bonds as well. So again, like I said, they're just different definitions for the same thing, and they're just a different way of looking at it. So if we look at this reaction, in this reaction, what you can see, and if we think of it from the Bronsted-Lowry sense of things, then water is an acid because it's donating a hydrogen, and ammonia is a base because it's accepting the hydrogen. Well, the ammonia is also a Lewis base because it is donating the electron pair. So that's a lot of times you'll see this. It's like the arrow is showing where the electron pair is going. The electron pair is grabbing this hydrogen. And then these electrons that were between the hydrogen and oxygen now only belong to the oxygen. So now oxygen has gotten an electron pair, so it's accepted the electron pair, so it's a Lewis acid. So both of these are acids and bases, and just a different way of looking at it. So there I wrote over it again. Nitrogen is a base either by gaining a hydrogen or by donating an electron pair, and the water is always an acid either by donating a hydrogen or accepting an electron pair. This is what I was talking about before. So a lot of times, many metal ions, especially transition metals, form what's called a coordinate covalent bond with other molecules that have. So these are, again, this is a Lewis base. And this is a Lewis acid because it doesn't mind getting electron pairs. So it's an electron pair acceptor, and these are electron pair donors. Sometimes we also call them ligands in this case. So these complex ions form where there's a polyatomic ion. So there's a central atom. So in this case, we have the copper 2+ is now the central atom, and it has surrounded itself with ammonia in this case, which are the ligands, and so it forms this complex ion. And we do one lab, we may have already done it before you listen to this, where we take copper and we add ammonia, and at first you get like a white precipitate, but then eventually if you add enough ammonia, you get a royal blue color, and that's this compound that is forming. It's a complex ion. So it's still ionic, so it's still soluble, and that's why we saw that bright blue. It wasn't cloudy at all because it's still ionic, so it's dissolved, but it's now attached to these Lewis bases, forming a different compound, so that's why the color changes. Notice that the charge stays the same. In this case, copper was a +2, and all the ammonias are neutral, so we still have a +2. This was what I was talking about. This is copper, just copper ion. And then if you start to add some ammonia, at first it gets cloudy, and that's actually copper hydroxide that starts to form. But after a while, if you keep adding the ammonia, the hydroxide leaves, and then we get this complex coordinate where the ammonia ligands are attached to the copper. So these complex ions, which are sometimes called coordination complexes, they're formed from a metal ion with a Lewis base. And the Lewis base, also called a ligand sometimes, are attached by these coordinate covalent bonds. So again, the complex is defined as a compound containing complex ions. So it has like a central ion and then other ligands attached to it. The ligand is always a Lewis base, which is an electron pair donor that bonds to the metal to form this complex ion. And like I said a minute ago, the charge of the complex ion always equals the sum, that should be of the charges of the ligands and central atoms. So if the ligands have a charge, you have to add those together. The formula of a complex ion is not really predictable. You have to determine it by experiment, so we can't know what it's going to do until we can find out. But amphoteric hydroxides, we talked about this just really briefly earlier, but because we talked about the OH bonds where it's like a transition, not the transition metal, but the metalloids. So an amphoteric hydroxide is a metal hydroxide that reacts with both acids and bases. So again, amphoteric means it can have acid properties and base properties. So for example, zinc hydroxide, now this is not an ion, but zinc hydroxide can react with strong acid. So what happens there, the acid pulls the hydroxides off the zinc, forming the zinc ion. So zinc hydroxide can react with acids. But what happens if zinc hydroxide reacts with a base? Zinc hydroxide here, if it reacts with a base, you can see that a coordinate compound complex ion forms. Two more, you've got the zinc hydroxide bond to the 2, you've got the +2 and the OH negative and the OH negative, but then you've got these 2 other hydroxides that attach as well. And you can see, this is what I was saying about the charge. This was neutral, and then we're adding 2 more negative charges. So that overall charge is -2. And this zinc, it's a different zinc hydroxide. Zinc hydroxide complex can form. And again, you can't predict this, and there's probably not going to be a whole lot of this on the test, but I just kind of wanted to talk about it. And this is similar to that copper that I was just talking about. So So if you have your zinc ion, or like we talked about before, you have that copper ion, well, that copper doesn't happen with the zinc so much, but the ammonia. But anyway, it's zinc. If you have zinc around and you add a little bit of a hydroxide, the first thing that happens is that the zinc hydroxide forms, which is a solid precipitate. But if you keep adding it, eventually you get to the complex. So the zinc itself would be colorless, and then we get a white precipitate, which if you keep adding hydroxide will dissolve, forming this clear colorless complex. And I wanted to talk some about these complexes because one of the labs that we do will be dealing with complexes. So how you know if it's a precipitate or an ionic complex is that ionic complexes are still ions. They're just complex ions, but they're soluble, right? So if there's a precipitate, then it's not ionic. Only if it's soluble will it be ionic. Other amphoteric hydroxides will work the same way: aluminum, chromium, lead, tin. And then finally, the last topic I wanted to talk about is qualitative analysis. And again, this is because we're doing a lab having to do with qualitative analysis. So it involves the determination of an identity of a substance, but what's the difference? Quantitative wants to tell you how much, but qualitative has to do with just identifying it. So what we're going to do is look at or analyze what happens to different metal ions when they're reacting with other ions. What are some characteristic precipitates that happen? When you form, so we've already used these terms, when you mix two things together and you have a solid at the bottom and then you have a liquid on the top, we know that's called the precipitate. And then the liquid above it is called the supernatant. And the supernatant doesn't have to just be pure water. It can have other ions. So ions that are dissolved are in the supernatant, and compounds that can't stay dissolved, that are not ionic, will be in the precipitate. And so what we can do is different metals will have different colors when they react with other ions. And so what we can do is create, and we're going to do this in lab, create a table to see how different reactions happen with other reactants, and then kind of figure out what's happening so that we can test an unknown and figure out which of the metals might be in there. So the figure on the next slide summarizes kind of an overall picture of all the ions. We're not going to do anything quite as complex, but you can get the idea. So these are kind of the 5 broad, this would have a whole lot of metals, and what we're going to be doing won't be so many. But you can see if you have a mixture of metal ions and you add some dilute hydrochloric acid, the first thing that if you get a precipitate, then you have one of these ions present, because these will precipitate in dilute hydrochloric acid. If it's not one of these ions, if it's any other ion, they will stay dissolved in the solution. So you can kind of, let me draw a little picture here. So here we have, we have our solution in here, and then we add the HCl, and we get a little precipitate. Well, what does that mean? That means that most likely there's either silver or mercury or lead down in this precipitate, and any other ions will be still floating around in here. So this would be the silver or the lead or the mercury. And then what we can do is we can actually filter it. If we pour that through here, then all the solid remains up here, and then the liquid now will could have any other ions except for those. And then we can further test it. So if we then add H2S in a mild acid solution, then if we get a precipitate this time, then it's going to be one of these ions. And then we filter it again, and any other ions will still be in solution. If we add the H2S now in ammonia, dilute ammonia, then these are the metals that will precipitate, and so on and so on. So let's just say, for example, and this is what's coming up on the next slide, but I'm going to talk through it now because I can't go back and forth. So let's say we have a solution, and now we're not going to worry about all of these, but I tell you, you possibly might have silver, copper, zinc, calcium, or sodium. I say you might have any or all of these ions present in solution. So there's nothing else, but these might be possible. So what could you do? So you take your solution and you add a little bit of dilute HCl. If you get a precipitate, then you know that silver's present. If you don't get a precipitate, then you know silver's not there. Then even if silver was present, it's precipitated out, so now it's no longer precipitated, so now we'll just have the copper and the zinc, possibly, and the calcium and the sodium. So now we do the next test. We add the H2S in dilute acid. Again, what happens if we get a precipitate at this point? What does that mean? We probably have copper. So if we get a precipitate, copper's there, but again, if no precipitate, that tells us we didn't have copper to start with. And so we kind of go down the line. So zinc, calcium, and sodium might be present. If we do the H2S and dilute NH3, what happens? And we get precipitate, that means we have zinc. But if we don't get a precipitate, zinc's not present. So we can go through each one. Finally, down here we might just have calcium and sodium. If we add one of these two solvents and we get a precipitate, we know calcium is present. If no precipitate, we know calcium's not present. And then finally, we only have the group 1A left, metals, and actually we know from our solubility rules they'll never precipitate, and so we can actually test it with like a flame test to see which of those metals, because those metals tend to give colors, and so there's other ways to test it. Now what happens though, you notice that my example only had one from each category. What happens if, say, you might possibly have silver and lead? I'll talk about that on a separate slide. You have to kind of then isolate. You isolate your precipitate and you test it further, and so it's separate now from the liquid, but you can save your precipitate and you can do other tests, and I'll talk about that in a minute. So this slide is just kind of going through what I just said. So what you start with, if you get a precipitate, you know silver's present. Separate them out again, add the H2S in 0.3 molar H3O. If you get a precipitate, copper is there, so forth and so on. Go through the zinc and then add the, find if calcium's there, and then once this ion is removed, only sodium might be present, and then it will never precipitate, but we can test for sodium by using a flame test. So that's kind of the idea. So like I said, sometimes more than one ion might precipitate out with a particular reagent. So for example, if you have both silver and lead and you were to add dilute hydrochloric acid, then both ions will precipitate. So how will you know if it's silver or if it's lead or if it's both of them? Well then, like I said, you can take that solid separate and do more tests on it. And this one we'll do, actually do in lab. So you can take, so that what you've precipitated, of course, is lead chloride and silver chloride. If you heat it up, then any lead chloride that's in solution will dissolve back into solution. So now that everything else is gone and you heat it up, if all of your precipitate dissolves back in solution when you heat it, then that tells you that most likely there's lead in there. If your precipitate stays, even after you heat it, then you know you have some silver present. Now, it's hard to tell if you have both, because of course if all of the precipitate dissolves, then that tells you you probably only have lead. But if you can't tell how much precipitate you have and you still have precipitate left after you heat it up, you know you have silver, but you might also possibly have lead. So actually you then have to, the lead might go in solution and you might not know if it's there or not. So then you have to test the solution one more time with chromate. And if you see a bright yellow precipitate, then you know lead is present. So anyway, you do further analyze each small portion of that overall chart by doing smaller tests, and you can separate them out as well. And like I said, we'll be doing a lab like this semester. So that's the end of this chapter. And what should you be able to do in this chapter? Probably those last analytical, the qualitative analysis won't be on the test, but it is really important information for a lab. So that's why I included it. So you should be able to write the solubility product expressions. You should be able to calculate KSP if you know the solubility, or calculate the solubility if you know the KSP. You should be able to calculate the solubility of a slightly soluble salt if you have a common ion. And you should be able to predict whether a precipitation occur, either given concentrations and the KSP, or given volumes and amounts and the KSP, using the Q to compare with the KSP. Be able to determine the qualitative effect of pH on a solubility. So if you know if the salt is the conjugate of a weak acid, then it will dissolve with more acid. It'll make it more soluble.